Okay, so let's continue. So last class we saw regular expressions. Then in the last class we saw what are called DFAs, deterministic finite automata. Some of you mentioned this idea of non-deterministic finite automata. So this is what we will introduce today. Let's first finish off some of the examples that we had last time. So here are the answers. So we wanted the DFA for the language consisting of all words over a comma b, where the number of a's is a multiple of 3. Right? So here is the DFA for it. So the states count the number of a's seen so far modulo 3. So this remembers that the number of a's seen so far divided by 3 gives remainder 0. Okay. From such a state, as long as I keep seeing a b, this does not change. The number of a's seen so far is still a multiple of 3. The moment I see an a, it becomes 3k plus 1. Okay. Then from here, if I see an a, it becomes 3k plus 2. As in the number of a's is some 3k plus 2. And then finally, one more a will bring me back to some 3 times k plus 1. Yeah. So for example, just quickly a, b, a, b, b, a, say. So I start at q0. Here I have seen 1a. Okay. So the number of a's modulo 3 is 1 and I'll be at q1. Here I'll go to q2. Here I'll stay at q2 because it's just 2 a's I've seen so far. Here I'll go to q0, q1, stay at q1, stay at q1, go to q2 and so on. So this will not be accepted because the number of a's seen is of the form 3k plus 2. Indeed, it is 1, 2, 3, 4, 5. Okay. So this is the DFA. So this will be rejected. Okay. This is the DFA for this language. So here are the other examples that we had mentioned. So one is B star A star. So here is the DFA. See, the initial state will be an accepting state because epsilon has to be accepted. You can keep seeing B's. The moment you see an A, you will have to see only A's. Okay, so that's how you read this automaton. Okay, this is the DFA. A plus B star, this is a set of all words. It's a single state. You don't have to remember anything. Just keep reading A and B. Okay. Now what about this? This is B star A plus A star B. So here is a DFA for it. So what does this say? So suppose I see, first of all, epsilon is not there in the language. Okay. So my initial state should not be accepting. Secondly, A, B are there in the language. Okay. So if I see an A, I go somewhere. If I see a B, I go somewhere. Now suppose I see an A. What else can I do? If I'm seeing more things, I have to be here. Okay, I can see some more A's and then a B. Okay. If I see a B, I can see some more B's and then an A. So this is also an accepting state because I can just stop after seeing either A or just B. Okay. So once again,
This will also accept
A star will be also accepted.
Yeah.
Oh, sorry. I made a
A
mistake.
square or A
And B
cube.
star also.
So no. So then this is not the right line. Wait. Let me keep this aside. So I see A. Okay. I see. Okay. I see the problem.
Excuse me, sir.
Yes. Tell me. Yeah.
Then B star, A star.
Hey, one second. Shall I just finish this and then come back to B star, A star?
Okay.
One second. So
So can we just not accept the first states? Then it will be fine. It will move forward.
yeah, but then you have to accept A, right? One second. Wait. What is the mistake I?
So the initial ones.
No. So suppose these are not. If I don't make them accepting, then how do I accept the letter A?
So but A is not there.
No.
Just A is not there.
It is there in the language, no? Because B star also has epsilon.
Okay, B star has epsilon. That's why. Okay.
Okay. So A. If I see, okay. If I see one more A, then I have to do this. Or I see B. Okay. One second. If I see B, if I see more B's, then I see more B's and then an A. Or from here I can go to an A. So is this fine? So I accept A, I accept B, I accept AB. Okay. I also accept any A power IB where I is bigger than or equal to 2, but I don't accept just A star. So if I see more A's, yeah, maybe there is a, so any comments on this? Is this okay? Do you agree with this?
Yes, sir.
Yeah. Okay. So yeah, that's why. So this was a mistake. Yeah, this is not. This is incorrect since it accepts A star. Okay. So do you understand this construction? Can you just say yes if you're okay with this, so that I know we are all on the same page, more or less. Okay, so some of you have not. Okay, good, fine. So these are some examples of DFA. So our next goal is.
Sir, before moving to
Yeah, sorry, I forgot about you. Yeah, tell me. Yes, Prasun, yeah.
sir, in B star, A star, like
Ah.
after in the Q1 stage, it accepts till it has A, and if it sees a B, so can we move it to rejection state to another state Q3?
You can do that. Yes, you can do that. You can add a B here and then some kind of a reject state. This is, and then just do A.
If we do not do that, so what does it signify? If it sees a B after that, where it will go?
It will just not. It will just get stuck. So it will just reject it.
So, sir, if it will get stuck in the acceptance state, that is Q1, so that will be accepted, no?
No. It has to read the entire word and then go to an accepting state.
Okay. So if it's not read completely, then also it's
no. Yeah.
Okay.
It has to read the entire word. So that's why the definition of the run has to be from, it has to read the entire word. So you have to label it for the entire word, and then in the end, it has to accept.
Okay.
Yeah.
Oh, okay, sir. Okay, thank you.
Okay. So yeah, so let's go to the next goal, which is, so we want to convert regular expressions to DFA. Okay, this is what our goal is. So far, see, we have seen some examples. We have seen this regular, we have seen for this regular expression, this is the DFA. For this one, this is. So how do we come up with an algorithm for converting regular expressions to DFA? Can we do that? Now the question is, why is this useful? Why should we at all do this? So this brings us to the second question that we had in mind when we started this module. That is, we want an algorithm to check if a given string W contains a pattern given by an expression R. Okay, so I give you some string. So it's like in a text editor, you have a string and you want to search for something. So you give a pattern. So does this string contain that pattern? Okay. Now the pattern is specified using regular expressions. Okay. So then how do we come up with an algorithm for this? Since we want to know whether the string contains R, we will consider the expression sigma star or sigma star for an appropriate sigma. Okay, so this is my string. I want to know if it contains R. So the string should satisfy the expression sigma star R sigma star. Okay. Secondly, suppose we are able to do this. We build a DFA corresponding to this. Okay. And then what? You just run that string on the DFA. Okay. Let's even assume that we get a complete DFA that doesn't get stuck. We add all the sync states, everything. Okay. So then you run the string W on DFA D. Now if D accepts W, then W contains the pattern R, otherwise no. Okay, so that's why this conversion actually gives us an algorithm for this pattern match problem. Okay. So any questions? Okay, good. So now this is going to be our next goal. How do we do this? So actually I made a point, it's this mistake has actually given me some extra thing, which is I wanted to say that converting regular expressions directly to DFA, we have seen examples, but there are some difficult cases. And indeed, there was a case where a mistake had been made, which is this one. A star B plus B star A. You had to use some kind of your own intuitive reasoning. It didn't look algorithmic, the construction. Okay. Now, what about this example? Try to find a DFA for this. So this is already done. So I'm first pointing out some difficulties in this algorithm, and then we will see how we are going to. So try to build a DFA for this, this language. Sigma star A sigma sigma, take sigma to be A comma B. So I'll just wait for a couple of minutes. So yeah, so there's a question, does every regular expression have a corresponding DFA? So this is indeed what we are going to prove. Like given a regular expression, we will be able to give an algorithm to convert it into a DFA. So yeah, I'll wait.
Excuse me, sir.
Yes.
So epsilon is not considered at all. Like if there is epsilon A, then we just consider it as A and do not pass epsilon from the states.
Yeah. You don't change state on epsilon. Is that the question?
Okay, got. Yes, yes. Thank you.
So yeah, so this seems a bit painful, getting a DFA for this. So let's anyway give it a try. Oops, sorry. So let's see. See, the goal is, I mean, it's a set of all words so that the third letter from the last is an A. Okay. Now, you need to kind of, whenever you see an A, you need to account for the fact that possibly after seeing this A, there will be only two more letters. If yes, I should accept. If not, I should redo. But then, after seeing an A, you may see yet another A. Okay, so you have to do the same trick for that A as well. Okay, so this is slightly tricky. So let me do this. So let's start with a slightly simpler one, which is, let's try to do this. Sigma star A sigma. Okay. So suppose I see an A. from my initial state. After this, if I just see some letter, in some sense, I want to stop. Like after seeing A, if I see some letter, I want to stop. But maybe there are more letters. And in that case, I should remember that I saw an A here. Okay. So, okay, let me draw this and then maybe. Okay. Now, in this case, I either stop, okay, and if I see another letter, say a B, and still I stop. If I see an A, it's still okay for me. Here, as long as I see a B, it is okay. Okay, so B here, A, I see an A, B. So each time I reach an accepting state, I reach from a state which has seen an A. Okay, so that is the point. So each time an accepting state, okay, every transition, say P to Q, leading to an accepting state, is from a state P that is reached on seeing an A. See, this is a difficult case. So that is the entire point of, okay. So you see this. Whenever I reach this state, so there are two accepting states. Now this one, I reach from here, which has seen an A. This one, I reach from either this or from this state itself, but this state is reached only on seeing an A. Okay, so let me just illustrate it by a few examples. So let's say,
hello, sir.
Yeah, B, A, yeah.
Sir, after reading B, we can again read an A.
Sorry, yeah, I missed that. Yeah, so from this state, if I read an A, should go back, no, not here. I should go back here.
To second one.
Yes. Yeah, correct, thank you. No, the initial problem was sigma star A sigma, but sorry, sigma star A sigma, I'm responding to a question on chat, but I'm first considering sigma star A sigma and already showing that it's a bit difficult. And then later, I'll leave it as an exercise. So there'll be 8 states for sigma star A sigma sigma. Okay, it will be a bit tedious, but we will see another way of getting it done. Okay, good. So yeah, so if I see BAA, okay, so what happens? BAA, it is accepted, it's fine. Okay, the other hand, if I see BAAB, this also should be accepted. So that's why I have BAAB. Okay, so this accepts all strings of this form that end with a B. This accepts all strings of this form that end with an A. Okay, so that's the meaning of this. So I'll let you, if you have understood, good, but if not, I'll let you just meddle around with it later to see that this is actually the DFA for this language. Now, so this is already tricky. It was not, it involved some extra reasoning. It didn't look algorithmic. So starting from here, how do you even construct this? Okay. Now let me tell you that sigma star A sigma sigma will be even tougher. Okay. So there you will need 8 states. Okay. So you can try to work it out. So the point being, in this process of converting regular expressions to DFA, there are some cases which don't look algorithmic in nature. Okay, it's not clear how to derive an algorithm from it. So this is where we will make use of an intermediate formalism called non-deterministic finite automata. Now, using this formalism, we will have an easier construction from regular expressions to NFA. And we will also see that NFA can be converted to DFA. Okay, so this provides a smoother algorithm for the conversion. Okay, so this is one motivation behind non-deterministic finite automata. So let's see what non-deterministic finite automata are. So NFA are going to be a relaxed version of DFA. So how is it going to be relaxed? See, in a DFA, we have some conditions. Single initial state and from every state on a letter, you can go to at most one state. At most one state. Okay. This is what we have seen. In an NFA, the single initial state is not required. You can have several initial states. Non-zero initial states. I mean, multiple initial states. Okay. And secondly, from a state on a letter, you can go to more than one. I mean, in addition to not going anywhere or going to a single state, you can go to multiple states. So okay, so these are the two relaxations. So you can again, 1 second. So there's a question about the previous thing. A, B. I forgot to draw the B transition here. Sorry. So if I have a B, what do I do? A, B, B. I have to go back here actually.
Excuse me, sir.
We already have a
second.
B transition there.
No, I mean, what, so for example, the Asif gives me an example, like what about A, B, B, A, B? A, B, B, A, B. Okay. So A, B, B, A, B. So, okay, because otherwise, how would you accept A, B, B, A, B?
In that state, we have two different transition for B.
No, it is B is from second to
Okay,
the
okay,
final.
sorry, I got it. Yeah.
Yeah. So I missed the B transition here. Okay. Yeah. Question. Thanks, Asif. Yeah. So
from the final state, when you're taking the A transition after
here.
after going through B, you could go to the second accepting state also for A.
No. See, then you will A will be accepted.
Yeah, but you can from there you can get back to B if you
No,
get
no,
to B.
no. See, you should not accept ABA. The word ABA also should not be accepted.
Oh, okay.
Right? Because the second last is B.
Okay, got it.
But sir, AB is in sigma star, right?
Fine. AB is in sigma star. Then A.
Okay, sorry.
Yeah,
Sigma does not contain epsilon. Only sigma star contains epsilon.
Yes.
Right. Got it.
Correct. Yeah. Good. Okay. Good. Yes. Okay. So we will see actually that drawing an NFA for that language will be very easy. Okay. So suppose we do this. Okay. What happens? So let's look at an NFA for A sigma star B. Okay. So what we are going to do is, from the initial state, we are going to read an A, and for the sigma star, we are just going to put A comma B, and then we are going to put B and go to an accepting state. Okay. It's kind of, it looks like this regular expression in some sense. Now, how does it read words? Okay. So when you are in this state, what do you do with the B? Do you go here or do you go here? So this is a question. So let me give some examples. So for example, if I have A, B, just this much. Okay. So let me give names to these states. Q0, Q1, Q2. So what are the possible ways in which I can read this AB? So starting from Q0, you read A, you can go only to Q1. Okay. From Q1 on a B, you can either go to Q1. Okay. The other option is, from here you could have already also gone to Q2. Right? Now, in this path, you reach an accepting state. Okay. Whereas here, there is no accepting state, which is fine. So as long as there is one path which is accepting, this is one run, as long as there's one run which is accepting, it is fine. Okay. So this was an example, I think, which was there in the last class also. So let's see some more examples. So let's say A, B, B. Okay. So I start with Q0, I read an A, I go to Q1. On a B, there are several options. I can either stay at Q1 or go to Q2. Okay. Now I have to read one more B. Okay. So far I've read only two Bs. Now from here, I can go to Q1. So let me make it a little bit. From here, I can read a B and go to Q2. From Q2, I cannot read a B. Okay. So this part of the run gets stuck. So the one which Q0 A, Q1, so Q0 A, Q1, and immediately which went to B in the second step will not be able to read the third B. I mean, will not be able to read the third letter. Okay, so that thing gets stuck here. Whereas if the automaton decided correctly to stay here, A, B, and then for the next B go here, then this is an accepting run. Okay, so in the deterministic finite automaton case, you will not have these branches, because there was only at most one state. You could either get stuck or you just, so it was a linear thing. Now it will be like a tree, the set of all runs, if you see. Okay, let's see one example where you will not accept. So let's say ABA. Okay. Now, why it will not accept? Maybe I can draw it from top to bottom. Okay, let's see. So Q0 A, Q1. On a B, what do we do? There are two options. Stay at Q1, go to Q2. Then there is one more A to be read. From Q1 on an A, I have to stay at Q1. But from Q2, I cannot read any more A's. Okay. But in every path that actually reads the entire word, the final state that is reached is a non-accepting state. So A, B, A, so I cannot draw something like this because here this was accepting, this was accepting. This is non-accepting. So this is not accepted since there is no run leading to a final state, leading to an accept state. Okay, leading to an accept state. Here, there exists a run going to an accept state. Okay. So if you look at the set of all words that have at least one run going to an accepting state, that will exactly be this thing. So if I take a word like this, the idea would be to stay here as long as possible, and the last be take this transition. Okay. Similarly, if I'm accepting this, I mean, if some word is accepted by this automaton, it means the last letter that was read is B. Okay. So this is there any question so far? I will show a couple of more examples. Okay, good. So just ping me on the chat if you have any questions. Okay. So here is a second example. So this is something which I said that it's not easy to draw DFA directly. If we had the option of having multiple initial states, because if I just had A star B, it's just, you just keep reading A's, and then when you see a B, you go here. That's all. If I had just B star A, it's just this automaton. Okay. But if I put both of them together and think of them as one automaton, okay, it doesn't work because there are two initial states. Whereas an NFA allows two initial states. Okay. So the automaton need not even be connected. Okay. This is one automaton. This entire thing is a single automaton. So this was Shuli's question in the last lecture. Okay. So what if we have...
This is A star B plus B star A.
Correct. Correct. So this is the NFA for this language, A star B plus B star A. So how does, so let me give names to this. So let me call it 0, 1, and let me call this 0 prime 1 prime. Okay. Now if I have a word of the form, say BBA, okay, so the run will start from 0 prime on a, okay, so there are several runs, one that starts at 0 prime and one that starts at 0. Okay, so let me, I start at 0, I start at 0 prime. If I read a B, from 0 I go to 1. From 0 prime, if I read a B, I go where? To 1 prime, sorry, to 0 prime again. From here I can't do anything because from 1 I cannot read any more letters. Whereas from 0 prime, I can still read a B to go to 0 prime. Then I can read an A to go to 1 prime. And then 1 prime is an accepting state. Okay, so this word will be accepted.
Sir,
yeah. Yes.
this is also accepting empty string.
Ah, sorry. So this should not be made an accepting state, this initial thing. You're right. You're right. Thank you. Okay. So the initial state should not be accepted. You should see at least one letter. Okay. So what if I take a string which is not of this form, say ABA? Okay. This should not be accepted both from 0 or 0 prime. So I start from 0 here, start from 0 prime. I see an A, I stay at 0 here. Here I go to 1 prime, and after that I get stuck. Here I go to 1 and then I get stuck. So I will not be able to read the last A. Okay, so this will be rejected. So it's the same idea as DFA, except that there will be several runs now. So in the previous case, the run looked like a tree because there was a single initial state. Here, it's like a forest. I mean, like there are several runs, multiple runs. Just think of it as you're enumerating all runs, possible runs. At least if one of them leads to an accepting state, you are happy. Okay. So there are two things: single initial state to multiple initial states. At most one transition on a letter to several transitions possible on a letter. So these are the two facilities offered by an NFA. Okay. So it's called non-deterministic because there are several options. Given a letter, given a word, you have several ways of looking at the computation of this automaton on the word. Okay. Now let's see. So this is the example sigma star 1 sigma sigma. I even took that. Okay. Oh, I just took 0, 1 just for a change. Okay. Instead of a comma b, just 0, 1 doesn't matter. Okay. So now how do we look at an NFA for this? Just look at the sigma star. So I keep reading 0, 1. And at some point, I'm going to guess the right thing, which is this is going to be my 1, after which I'm going to see exactly 2 letters. Okay. So this is the NFA for this language. Now, what is the NFA for the other sigma star 1 sigma? The NFA for that will be 1, 0, 1. Okay. So why is this? Let's just look at an example. So if I take a string 0, 1, 0. Okay. Let me give now names 0. No, 0 is bad now. Q0, Q1, Q2. Okay. So I start from Q0. If I see a 0, I have to stay at Q0. Now from Q0, if I see a 1, I can either go to Q0 or I can go to Q1. From Q0, if I see a 0, I stay at Q0. From Q1, if I see a 1, I go to Q2. And this is an accepting this is an accepting run. Okay. On the other hand, if I just had say 0, 1, you will have this thing like Q0, Q0. This is going to Q0. This is going to Q1. Both of them are non-accepting, so this will be rejected. So in some sense, this non-deterministic, this NFA is guessing that when I take this transition, after that there will be only 2 more letters. So that is giving me one possible run which is accepted as long as the word is of that form. Okay. So this is an NFA. Now let's do some exercises. Okay. So we saw 3 examples which were difficult in the DFA setting. We did an NFA. So now try this example. You can either draw a DFA or an NFA as you wish. Okay. And then we will see what are the questions that arise. Okay. So I'll give some, say 5 minutes. Okay.
Excuse me, sir. So for an NFA, it runs through all the possibilities, or it chooses random some?
No. It runs through all the possibilities, and even if there is one possibility which is good, it will accept the word.
Okay, like an OR. Okay.
Yes. Yes.
Okay, got it.
So yeah, let me start explaining. Yeah. The first one, even number of zeros or odd number of. So this is like so Rahul's comment came at a good time about the OR. So for the NFA, you have one part of the automaton which is going to look at even number of zeros. So it will. And then one part of the automaton which is looking at odd number of ones. Sorry. Okay, and this entire thing will be one automaton. Okay. Now, if I have a word which has say even number of zeros, then the run that starts from here will be accepting. Some words may have both. Okay, that it may have both an even number of zeros as well as an odd number of ones. In that case, there are multiple accepting runs. That's fine. As long as there is a single accepting run, it's good. Okay. So any questions so far? So can you say yes if you understand, if you understood this automaton? It's a bit quiet. Okay. Fine. So what is the second thing? 0 star, 1 star, 0, 0 star. 0 star, 0 star, 1 star, 0, 0 star. Okay, so let me just draw it. 0 star, 1 star, okay, 0, 0 star. This is not entirely correct because I also need to do 0. Okay. One second. So, one second. So there's some question. So what is this question? So if there is no, see, if there is no accepting state in both the automata, then the language will be empty. Is that the question? Wait. Okay. So why was this? So in this case, see, I needed 0 star.
Sir, no, in the previous case.
Okay. Wait. Let's go back to the previous case. So what is the question?
Sir, what if some word is not accepted in both of the automata, any of the automata?
Then it will be rejected. See, what is a word which will not be accepted by both of these automata? It has odd number of zeros and even number of ones. In that case, it will end up here and here.
Okay.
And we have to reject it because it does not belong to the language. Right?
Yeah.
Is that clear? Okay. So yeah. So a word which is rejected, all the runs will be non-accepting. So in this case, both the runs will be non-accepting, which is what is intended. Okay. So now coming back to this, so see, if this 1 star might as well be epsilon. Okay, so after this, I might just read 0 and then do this. Yeah, or I can do this, do some 1 star and then do a 0 and do this. Okay, So this is like the translation of this expression to this. So is this fine?
Sir,
Yeah. Yeah. Tell me. Yeah. Okay, so there seems to be a problem. So Shuli, you have a question? Okay, okay. I think there's some problem with the internet. Okay. Any questions on this? Any other questions on this?
sir, am I audible?
Yeah, yeah. Now, yes. Yeah.
Sir, will there be any transition from the first to second only 0?
No, 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 no. From here to here?
Yes, sir. Because, sir,
Mm.
uh, if the 1 star is epsilon, for that case.
So that is why I added this thing,
Oh, okay, 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 sir. Okay, got
right?
it.
So from here, I just went to this. I mean, I just did this and jumped to this part.
Yes, sir. Actually, I added both. That is. Okay, sir.
So no, no. But if you add both, so how do you just accept 0? This is singleton 0. See, because that should be accepted, right? So in this case, it will get accepted. Shuli, do you get my question? If I add a 0 here, then and not this, and if I don't do this.
No, no, that is necessary.
Okay.
I
Okay.
added one more.
Okay. Okay. Fine.
0 link.
Okay.
So can there be multiple automata for the same language?
Yeah. Yes. Yes. There could be. So, for example, I mean, see, I can always do crazy things. Like I just do one and then do something, and have nothing, no accepting state, anything from this side. And this I can do whatever I want there because it will not affect the acceptance.
Okay, okay.
Okay. So, yeah, but it's a good question because then there's a question of can we get a small automaton, things like this. Okay, as small as possible. So these kind of questions are outside the scope of this course. Okay, but it's possible to look at it in the DFA case. Okay. Anyway, so what was the next? W ends with 0, 0. Sorry. So what is the NFA for this? This is, I just do 0, 1, 0, 0. That's all. So at some point of time, when I'm reading the word, the run just says that I'll just see 0, 0. So for all, I mean, if I give a word, if the word is ending with 0, 0, then there will be a run because the run which takes this transition in the last to last 0 will lead to an accepting state. Okay. And if it does not end with 0, 0, there is no way you can reach this accepting state. Okay. So I hope you get a feeling of what an NFA is. Okay. So I have to give you a formal definition of NFA and a formal definition of its acceptance. But instead, what I'll do is I will write this down and I will upload it in the slides. So you can check it later in your own, at your convenience. But instead, let me give the conversion from regular expressions to NFA. So how do we, so now that you understood this NFA, we are going to look at regular expressions to NFA So you remember the picture that from regex, we want to go to NFA. From NFA, we want to go to DFA. So today I'll just do regex to NFA. I will need one more lecture. I will compensate it I'll talk to you later. Okay. So let's see regular expressions to NFA. So how do we do that? See, from the expression, from the examples, you see that there is some kind of an algorithm. Okay. See, first, what are the basic regular expressions? A, which is just a singleton. Okay. I mean, any A in sigma is a regular expression. Epsilon and empty. These were all the basic regular expressions. From this, we were applying other operations to get more regular expressions. So what we will do is we will first give NFAs for each of these basic ones. And then we will inductively show that if I have an NFA for R1 and R2, how do I get the NFA for R1 dot R2, for R1 plus R2, and for R1 star? Okay, so this is what this like an inductive algorithm that we will be using. So first, for basic regular expressions, it is easy. So for A, it is just this is my NFA. For epsilon, this is my NFA. And for empty string, this is my NFA. Just don't make any state accepting, but we need to have an initial state. Okay. These are the basic regular expressions. We have an NFA for all basic regular expressions. Good. So now we have more complex regular expressions, right? So and how do we build complex regular expressions? There is R1 plus R2. Okay. Okay, fine. Let me start with R1 plus R2. Yes. Now suppose we have, constructed NFAs for R1 and R2. What is the NFA for? So how do we get the NFA? So this is assuming that I'm assuming that there is an NFA. So how do we get that NFA? This is where we will make use of the fact that there are multiple initial states. Okay. So you look at the NFA for, suppose this is the NFA for R1. So call it N1, which is the NFA for R1. It will have some number of initial states and some final states. Okay. Now we also have an NFA for R2. So there will be some initial states in general and some final states. Now for the plus, we just have to look at this entire thing as one NFA for R1 plus R2. This is like that A star B plus B star A. We first did A star B, then we did B star A, then we looked at the entire thing as one NFA. Okay, so this takes care of the union operation. Please type yes if you understood this.
Sir, within N1, there can be multiple initial states.
Yes. Yeah.
Okay.
So it's an NFA. N1 is an NFA. N2 is an NFA. Now just put these two things together to think of it as one NFA. That will be the NFA for R1 plus R2. So remember this. This is why I said remember this. See, if I had this A star B, A star B was my R1, say, and B star A is my R2. You remember that we drew an NFA for A star B, which is this, and we drew an NFA for B star A, which is this, and then we thought of this as one NFA. Okay, so this is the same idea which is generalized. Okay. So
Yes, sir.
now, okay. So now let me go to the next operation, which is what? R1 dot R2. As in like things like A, B, A, B, A, A. How do you get that? A dot B dot A, right? So I can also do this dot. R1 is one expression. So suppose I have N1, which is for R1, and I have N2, which is for R2. So if a word belongs to R1 dot R2, say, look at this word. Suppose this is my word. Okay. If it belongs to R1 dot R2, then what does it mean? So there is a part of the word that is accepted by N1. And from that point on, this part of the word is accepted by N2. Right? So now some way we have to tie this N1 and N2 together so that when it is seen as a single NFA, it is able to read N1 and then jump to N2 at some point and start reading the second part of the string. Okay, so how do we do it? So people who have already seen this construction, please don't respond. But if you're seeing, so anyone, any ideas like how do we? So I start reading my string. Okay. So N1 will have some initial states and final states. Somehow, after I reach some final state, I should have the option of jumping to this automaton and then reading the next part of the string.
Connecting them by an empty set or something.
Yeah, so we don't have this epsilon facility. We don't have an epsilon facility. So instead, what can we do? See, this is my, say, suppose this is one initial state. Okay. And from here, suppose on an A, I go to this state. Okay. See, the idea is to use, yeah, correct. So the idea is to somehow use this as an initial state for this automaton. Right. So somehow, suppose I reach this state by reading a B. Okay. And from here, on reading an A, I will add a transition that goes here. Okay. For every letter, like suppose on a B, this goes here, then I will add this transition. I will do this for every pair of final and initial states. So for every final state here and initial state here, I will stitch this together. From this final state, I think of this as an initial state, and then I go here. Okay. It's not done yet. What we should do is these things can no longer be final states because I want to go here and then do the, I want to accept it over here. Okay. So here there is a slight detail. Wait. So anyway, let me write it properly. So what we do, so from every final state Q1 of N1, add a transition Q1 A P for all transitions P0 AP, okay, where P0 is an initial state of N2. Suppose I do this, okay, so I'll give you examples, guys, so don't worry. For the moment, I'll just finish the, okay, I do this, okay, and secondly, make all final states of N1 as non-final, as a non-accepting. Keep only the accepting states of N2 as accepting. So there is one thing which is left, but modulo that, do you get the idea? So I keep doing this and then I have to jump here. Okay. There's one problem with this construction. Can anyone tell me?
Sir,
Hmm.
N2 can accept an empty string. So if we make every final state of N1 non-accepting, then it will be a problem.
Exactly. That's right. Exactly. So if this initial state was accepting, okay, and then this was, and then we just remove this to be since we are simulating this initial state with this, and if we make it non-final, then it will be a problem. Okay. You make all, so then what we should do is we have to make it as non-final only under certain conditions, which is none of the initial states are, okay, wait, let me try to, yes. So only if none of the initial states are non-final, then you make this, okay? Only if, let's say epsilon is not in the language, is not in N2, okay? Which essentially means that none of the initial states is a non-final state, is a final state, okay? So yeah, so I can see, even though I don't see people, I don't know, I'm somehow sensing a silence. Yeah, correct. I see this. What I'll do is I'll give an example for this in the next class. Okay. Now let me just finish the okay. Or maybe let me just do an example. Okay. Say suppose R1 was A and R2 was B. Okay, just to start off with. What will I do? R1 will just be like this. The NFA for R2, the N2 will just be this one. Okay. Now what is R1 dot R2? AB, right? What is the previous construction? So this is one NFA, this is one NFA. What we will do is from this state, that is from this state, maybe I'll draw it here. So let me draw the things again and then, so this is Q0, Q1, P0, P1. Okay, this is what we start off with. So then let me draw it again. Q0, Q1, P0, P1. Okay. The first thing that I will do is, see from this initial state, on a B, there is a transition. So that is the first thing I'll do. From here, I will put this. So what does that mean? From here, from this state on a B, we will add this. Okay. So good that I did this example because I missed one step. Okay, B. The second thing that I'll do is I will remove this as a final state because epsilon is not there in the language of N2. Okay. I should do a third thing, which is this should no longer be an initial state. Okay. Unless epsilon is there on this side. Okay. So it's a symmetric thing. So I see. So I kind of bypassed one step and this is making it a bit difficult. Okay, let's see. And then make all initial states of N2 as non-initial if epsilon is not present in N1. Okay, so that's what we did here. If epsilon is not present in N1, we just removed this thing as being an initial state. Okay, so this is my automaton for AB. Okay, see, it has some extra states, but we don't care. Okay, it's like you can even like remove states which cannot be reached from an initial state, but it's okay. This is the final automaton that we get by this construction. Okay, so is this for A, B clear? So I got, this is an NFA for A, this is an NFA for B. And how do I get an NFA for AB via this? From every final state of N1, I draw transitions to all outgoing edges, outgoing transitions from the initial state of N2. So here there was a single thing. So I just drew this. I make this non-accepting since epsilon is not there in this language. I make this non-initial since epsilon is not there in this language. This is the algorithm. But what we will do is in the next class, I need one more lecture. I will try to explain this with some examples. Okay, so that we will then see that from regular expressions, you can actually construct NFAs. Okay, so we are yet to do the star. So we have done R1 plus R2, R1 dot R2, but we have not done R star. Okay, so this I will finish in the next class. So try to digest this in the meantime. So what you can do is take some examples of R1, R2, you draw NFAs for them, and then apply this set of rules to see whether you get an NFA for R1 dot R2. See, by now you will be able to get an R1 dot R2 directly, but you can try to, in order to just understand this algorithm, you can try this out. Okay, so this is the summary for today. We have seen NFAs and part of translation of NFAs, sorry, of regular expressions to NFAs. Regular expressions to NFAs. Okay, so I will finish this off in the next lecture. So, so next week is not a very good time for me because of some workshop that is happening. Is there a possibility of having a lecture this weekend, like just one lecture? That will be the last lecture. Can someone coordinate with the rest of your batch and then say, for example, 3:30 p.m. on Saturday? Saturday is what? Today is 28th, 30th. I will finish off everything. so that then in the next week, next week, you can have a tutorial, and then we will have a final exam in the week after that. Because the other course is starting, the second part, I mean, the next 2 credit course is starting next week, right? Is that right?
So it's starting on 1st Feb. Not 1st Feb, the coming Monday. Whatever it is.
Yeah, it is. Yes. So, which means that we have to stop soon. So, let's say Saturday 3:30 to 4:45, or maybe up to 5. I may go on for 15 more minutes. So 3:30 to 5. For the moment, let me fix that. I'll also send out a mail. If someone has a serious problem, let me know. But you also see that if you cannot make it, you also have the recording. So yeah, so I mean, this is just one lecture that I need, and then I can finish this picture. Okay, and I'll also do a bit more gentle, gentle introduction to this construction. If you have understood, it's well and good. If not, we will see some more examples which will clarify this construction. Okay, but I hope you get the feeling of what DFAs and NFAs are, and the point of this regex to NFA to DFA. Okay.
So we'll be doing NFA to DFA in the next class, right?
I would like to do, okay, this see this NFA regular expression to NFA. There is only one more step left to be done for the R star. Okay, so after I'll probably do that in the first half an hour, and in the next 1 hour I will try to do the NFA to DFA. So regex to NFA to DFA. So this the first part I'll try to finish in 30 minutes, and this one I'll try to do in an hour. I'll at least give you an idea of how it goes. Okay, whatever is possible, and then maybe in the tutorial you will get some more examples and it becomes clearer. Okay. Any questions? But the class is over. If you can feel free to leave. Any other questions? I'll just answer them.
So
yes,
I have a question. In A star B plus B star A DFA that you had made.
The DFA that I made. Okay. This is the NFA. Where is that? This one, yeah. Okay.
So why is it wrong? The right side.
This one, okay. So see, this also accepts AA.
Oh, okay.
Yeah. So we had to be a bit more careful. This was not, this quick thing was wrong.
Okay.
Okay. Any other questions? Okay.
Sir, can you please explain that sigma star A sigma DFA?
Okay.
Once more, actually.
This
sir.
one. Right? This one, right?
Yes,
Sigma
sir.
star
Yes,
A
sir.
sigma. Okay.
So, sir, why it is going backwards?
This
I
one?
don't understand.
Wait.
Yes, sir,
Okay.
this.
See, let's try to see, what do we want? Like, we want to read an A, and then we want to read some letter and then stop. Right? Now, so we want to read an A, then read some letter and stop. Hopefully this one is the last thing that is seen. But what if there are more things? Okay. And in that case, we have to make a distinction between what we are reading, either A or B. Okay. So that's why we first had this division into 2 states. Okay. A, B, you accept. A, you go here. The extra condition is that as long as you keep seeing an A, you stay here. Whereas if you see an A here, you have to go back here because you come here with a B. So for example, suppose I see A, I see B, and then I see an A. I should go to a non-accepting state. Whereas I see A, say B, I should go to an accepting state, right? So you understand that from here on an A, you have to go here. Is that clear for a start?
Yes, sir.
Yeah. See, now from here on a B, where do you go? Okay. See, when you come here, you have seen A, B. Okay. The last two letters that you have seen are A, B. So you come here either by doing this and this or by doing this and this. Right. So the last two letters that you have seen is A, B. Okay. So I should have given names to the states. So this is A, B. The last two letters that you have seen is A, B. Now, if you see a B, okay, so you will be reading A, B, B. It's like you have reset everything.
Yes.
Because then you have to once again see an A and then see a B.
Okay, that is not accepted actually, ABB.
No, it's not be accepted because, right? So it's like, so I should have, so the names of these states, you can call this QAB, QAA, QA, and let's call this Q epsilon, in the sense that you have not seen anything at all. Like you are yet to see anything.
Yes, sir. Now I can understand. Like it should end in A or AB.
Exactly.
Yeah.
So I see that this makes it much simpler to, use it.
Yes, sir. Thank you, sir.
Yeah. So you have to remember the last two letters that you have seen. So in the sigma star A, sigma, sigma, you have to remember the last three letters that you have seen. Okay.
Yes, sir.
Okay. I'll write this part so that people who miss this. So remember the last two letters. Let us see. And then, yeah.
If N2 has two initial state and one is final and other is not, then what should I do with the final state of N1?
You should keep it final because epsilon is there in the language. See, if N1 has, sorry, where is this? See, if N2 has one initial state which is accepting, it means that epsilon is there in the language.
Yeah.
Right? So as soon as I read N1, I should also accept the word in N1.N2.
Right.
So that's why I said make all final states as non-final if epsilon is not in N2. Make all initial states of N2 as non-initial if epsilon is not in N1.
So I want to give an example. Think that R1 is A and R2 is B star plus AB.
So why star now? Okay, fine. Let's try it out. Okay. Wait. So R1 is
A and R2 is B star plus AB.
Plus AB. Okay. So let's try
then this is N1 and N2 is that is B star and other one is A. Then what should be R1 R2?
So R1.R2 is A B star plus AAB. Right?
Yes.
So first step, I will first look at this. See, for this one and this one, okay, so I'll just put a B here because this has a transition on a B going back to B. Okay, and here I will put an A. Okay, so now epsilon is there in R2.
Then A will be the A dot epsilon.
Yeah, so I leave this as final. Okay, And now epsilon is not there in R1, so I don't make this initial. So I will remove these things. Okay. So now look at the automaton. If I draw it carefully, this will be A, accept, B, accept. Sorry, what was this? This is A. And then A, B.
Yes, I got it. Thank you.
Yeah.
Sir, in case of
Huh.
A sigma sigma, there should be 4 final states.
Yes.
A, A, B, ABA, and ABB.
Correct. Yeah, you're right. Yes.
Okay, sir.
Okay. Okay. Any other questions? Okay. So if not, so let's then let's then meet on Saturday. Okay. I'll finish this off. Okay. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Yes. Thank you.